record so that they can watch it. Okay, awesome. Okay. How did you think the quiz was? Was it all right, or was it? Or, I feel like a lot of people are having trouble with with titrations and with buffers. So I was wondering how you're feeling and if the quiz was all right and everything.
Yeah, no, the titrations, yeah, I definitely have to somehow study that between like today and like the rest of the week because I have no idea what's going on with those. But I feel like the rest of the test was like okay. Like I looked through it and like some things I did get correct. I feel like more things correct than like I thought I would.
That's good. Yeah. So we can. I like didn't put one of the full like titration type problems because we like this was already pretty long, and because I like didn't realize you guys were going up until titrations until like Wednesday after I'd already made the exam. So if you want to go through like the titration problem that Dr. Martinez went over in class, I think like on Wednesday maybe, or maybe it was on, I don't know. She should have told us like where it went through each part of a titration during our staff meeting on Wednesday, but I'm not sure if she already lectured that. I assume she did. With like, I think it had like a weak base and a strong acid. It was like,
Yeah, it was during lecture. Yeah, if we could go over that, that would be cool. Because yeah, I
yeah,
have no idea what's going on with that.
yeah, we could all go over it. Okay, so we'll just start off with like the going over the quiz like usual too. Okay, so for the first one here, it was I think there was one that was pretty similar to this last on the last like mock exam I made where it was like a phosphate and like an arsenic maybe compound. And so this one's kind of like a different compound with the same idea. So it was like which one's the stronger base, S2 negative or Se2 negative. Oh, awesome. Okay. So how did you think the exam was? You can type in the chat if it's easier for you to.
Were you talking about the mock exam you're talking about?
Yeah. I think that I was in the sorry if I say your name wrong. Paola, is that how you say your name or do you pronounce it differently?
No, Paula. It's okay.
Paula.
But it's okay. Yeah.
Sorry. How was the mock exam? Was it all right?
It was like in the middle. Like I feel like I was good with some things, like for example, determining the acids and bases. I think that was like if it's going to be like an acid or base based on just like the chemical composition of it. I think I was now I know that I'm kind of more confident in that. But when I get to come with if this is going to become like a salt is going to become acidic, neutral, I need practice on that. And I still with the buffers. I still need to become a little more confident with that. And yeah, I think titration since it was a recent something new is I still need to get there.
Yeah. I was just talking to Kelly before you joined where I was saying like there's not like one of the full titration problems on this mock exam because it's like so long to go through. But I'll probably go through the one example that Dr. Martinez did in lecture with like it was like a UDO problem, and I think that she like did the equivalence point solution. We can like go through the whole titration if you want to. I think that Kelly that would be helpful. So if you want to stick around and go over that, we can go like try to go through titrations a little bit because I think that up to titrations will be on your exam on Wednesday. Okay, so for the first problem though, it was just like which is a stronger base, and so it kind of goes back to like your like acid strength rules. And so if you remember like how strong acids, like how if you have like HI for example, if it dissolves or HCl, the Cl minus or the I minus, it really is like so super weak base because it doesn't need a proton because that strong acid dissociates completely. And so that idea holds for all different acids and bases. And so the stronger the acid, the weaker its conjugate base. And so for this problem, just try to think about like which acid would be stronger, H2S or H2SE. And so because the periodic trends for binary acids are that like as size increases down a period, or sorry, down a group, the bond gets weaker and the acid gets stronger. And as you can see, Se is lower in the group than S. And so H2SE would be the stronger acid. H2S would be the weaker conjugate or would be the weaker acid. And so if you think that they're conjugate bases, the stronger the acid, the weaker the conjugate base, it means that sulfur, since it's the weaker acid, will have the stronger conjugate base. And so H2 or S2E, oh my God, S2 negative would be the answer for that one, for what is the stronger base. Does that make sense? Or do you guys have any questions about that?
Is this kind of like because I use the concept of the, I'm sorry, I use the concept, trying to pull up my notes.
Take your time.
Is this the same as like the binary acid and oxyacids kind of? Because I use that concept of, if it for like, I think they both have the same kind of concept in a sense. So yeah, that's why I was able to pick S minus because it's more electronegative.
Yeah,
than S.
it's almost like the inverse of the acid strength trends. So like your acid strength trends are that as you go across a period, as electronegativity increases, your acid's going to get stronger because the bond's more polarized. But as you go down a group, the acid is going to get stronger because the bond's going to get weaker because the atom is like the size is increasing so much. And so it's like almost like the inverse for bases, because you kind of think about it in terms of like their conjugate acid and whether it's going to be stronger or weaker. And I guess another way to think of it is like which one can hold like the charge better, like how you were saying with like an electronegative atom. So I guess it's a good way to think of it too, where like as electronegativity increases up a period, like up a group, the stronger the base because it can hold on to that negative more easily. And so that would be a strong, or I guess actually, no, kind of inverse. Sorry, that was a good way to put it. So as you go across a period, you'd still have the stronger the base because of the stronger electronegativity, or sorry, the weaker the base because of the stronger electronegativity, because a base, if it's really electronegative, it can hold on to the negative charge really easily. And so it doesn't need a proton to be stable. And so it's almost the opposite trend, where the smaller the electronegativity, the weaker or the stronger the base, because the more it needs that proton to carry the negative charge. Does that make sense? So it's kind of like the inverse of acid trends. Okay. So then this one was going back to what you just talked about with acid, the acid strength trend though. So this was just like picking the stronger acid from each pair. And so H2SO4 would be the stronger out of this pair because it has more oxygens. And then in this case, the HClO would be the stronger acid because Cl is more electronegative than Br. And so it would cause like the electrons to be like pulled away further from that HO bond. And so that H would be able to leave more easily. And then for H2O and HF, because they're in the same, because oxygen and fluorine are in the same period, you'd have to look at electronegativity. And since fluorine is more electronegative, the bond's going to be more polarized. And so HF would be your stronger acid here. And then this one, the CCl3 COOH versus CH3 COOH is really similar to the number 2 here. And then again, like it just goes back to like if you have those really electronegative like elements present, they're going to pull the hydrogen or the electrons that's in that like hydrogen oxygen bond further away. And so it's easier for that proton to leave. And as you can see, hydrogen or like chlorine is like way more electronegative than hydrogen is. And so the CCl3 COOH is the stronger acid. And then finally, H2TE versus H2SE is kind of like just like one of the normal binary acid trends where you have them in the same group. And if they're in the same group with the same column, you want to look at acid or atomic size in comparison to acid strength. So the larger the atom, the weaker the bond and the stronger the acid. And so in this case, H2TE would be the stronger acid. Do you guys have any questions about that? Or any of those, or any of the trends, or why it is what it is, or anything like that? Or is this good?
Yeah, I just have a question on like the last one. How come you look at atomic like size opposed to electronegativity?
So I think that the easiest way to think about it is like if you're going across a period, you do electronegativity because their sizes, even though their sizes are like getting smaller across a period a little bit, the electronegativity is really changing a lot from element to element across a period, and they're not getting a new electron shell. But as you're going down a group, the difference, like the effect of the atomic size is so much greater than the effect of the electronegativity change, because like you're adding an entire electron shell as you go down a group. And so the easiest way to look at it, I think, is like if you're going across a period, look at electronegativity. If you're going down a group, look at atomic size.
Okay.
And how come it wasn't SE and it was TE? Because when I did it, it was like I saw it as that SE was more electronegative than TE.
So it's because of the atomic size again. So as you have like the larger the size of an atom, because like atomic, like the bond strength is kind of measured. If you remember like maybe doing this a little bit with like lattice energy, you have like, so this is your hydrogen, it's really small, and then you have like your large, like chlorine, for example. The bond is like measured from nucleus to nucleus. So as your like atoms are getting larger, that bond is getting weaker, and it's easier for that hydrogen to leave because the bond is so weak. And so it kind of comes back to like, how big is the effect of atomic size versus how big is the effect of electronegativity, because they're opposite trends. And so that's why like across a period, as you go across a row, as you go across a period, across a row, electronegativity is more important because they all have the same number of electron shells. But as you go down a group, because they're gaining an entire electron shell, the effect of atomic size is much more important than the effect of electronegativity. Does that make sense?
Yeah.
Okay. And then the next one was a complete table, just like using some of the equations that you have had to learn for like H3O plus and the autoionization of water and stuff. And so the way that you solve these ones, so when you're given the OH concentration, you would find the concentration of H3O plus using the autoionization of water. So if you guys remember that equation, it's the one where it's Kw, which is just, you remember like equilibrium constants? The Kw is just like a special case of an equilibrium constant specifically for water at 25 degrees Celsius. And so Kw equals 1.0 times 10 to the negative 14th. And then Kw equals the concentration of OH minus times the concentration of H3O plus. And so you would use this equation to solve for both the H3O plus concentration from OH minus, and you would use it to solve for OH minus if you were given H3O plus concentration. So for this one, to solve for H3O plus, you would do 1 times 10 to the negative 14th divided by the concentration of OH minus. So you would do 1 times 10 to the negative 14th divided by 6.8 times 10 to the negative 7th. And you get 1.5 times 10 to the negative 8. To solve for pH, you would use the equation that is pH equals negative log of your H3O plus concentration. And so if you did that with the concentration of H3O plus for this problem, you get a pH of 7.8. And let me increase the size of this a little bit because it's kind of small. So you get 7.8. And then because the pH is because the pH is above 7, and also because the concentration of OH minus molecules is larger than that of H3O plus molecules, this solution would be basic. And then you should do a slightly different approach for the next one, because you're given the pH but not the concentration of H3O plus or OH minus. So if you look at this equation for pH, it's pH equals negative log of H3O plus. But to undo a negative log, you do 10 to the, and so, to undo a log, you do 10 to the, like how you would do like the Arrhenius equation. If you remember, you would undo an E raised to the, you would undo it with a natural log. this is just a log base of 10 instead. And so to get the H3O plus concentration, you do H3O plus equals 10 to the negative pH. And so in this case, you do 10 to the negative 2.63, and you would get a concentration of 2.34 times 10 to the negative third molar H3O plus. And then you would do the same thing you had done before up here when you used your autoionization of water. And so you would divide 1 times 10 to the negative 14th. You would divide that by the concentration of H3O plus, which is the 2.3 times 10 to the negative third. And you get a concentration of 4.27 times 10 to the negative 12 molar of OH minus. And then again, because kind of how we did this for the last one, because your pH is way under 7, and because the concentration of H3O plus is a lot larger than OH minus, your solution is acidic. Do you guys have questions on any part of solving for this? I know it's kind of like a lot in one question.
Yeah, I have one question. So for the H3O concentration, I got it marked wrong in the sense that like I didn't round properly. So I guess my question would be like, how do you know how to round? Because I did like 2.3 and it said it's 2.34, or like for the OH one, I did 4.3 and it's supposed to be 4.27.
So I guess that like if you just keep sig figs here, it would be like because 2.63 has 3 sig figs, then I guess that would be 3 sig figs, or 2.34 times 10 to the negative 3. Hopefully in an exam though, she would just give you multiple choice for these kinds of questions, and you wouldn't have to like actually figure out number of sig figs.
Yeah, I really hope, because I got the answers, but they're close, so they're like, and I got them wrong in a sense, because instead of 4.27, I got 4.25 for and then it was wrong, and for the pH I got 7.89, and it was marked wrong.
So yes, I guess like as long as, I would think that I really wouldn't expect them to do like something like this where they have like the fill in, because I don't think they really like to grade your questions like usually if you guys have to have a question where you're writing an answer, it's an essay question because they want to check your conceptual understanding. So I don't think they would ever really have you do a problem like this or have to like fill in numbers like this, because I think they would have so many issues like that for sig figs. But I guess that's why I had like put the answers in just the number of sig figs. But like when I do it on the computer, I have to just type in all the possible answers. So I just put in the answers that I got, but it's totally possible that you got the answer right. It just had a different rounding issue or something like that. But do you have any questions about how I solved for any of the things or anything? At least it sounds like both of you guys knew how to do the calculations, and that's all that really matters.
I'm good.
Okay, I'll move on then to the next one. So the next one I thought was like kind of I get all these questions from the textbook, and I thought the next one was like kind of a good like thing to keep in mind. So KW, if you remember like last chat or like chapter 15, so it was a while ago, but your last exam when you did like equilibrium, if you remember like your K value would change at different temperatures. And so KW is just a specific case of your equilibrium constant for water at 25 degrees Celsius. And so at different temperatures, your KW is going to change. So they might have talked about this, I know Dr. Muniz brings it up a fair amount, at least when he talks to the LAs, about how like your pH scale will kind of change if you're working at body temperature, or like if you're doing biology, you'd be working a different thing because body temperature is more like 98 degrees Fahrenheit or 37 degrees Celsius. And so like you don't always work with 25 degrees Celsius for like figuring out different stuff for acids and bases. And so this was a kind of a good example of, although like not to confuse you guys, because like if you ever got a table like this, it's like assume all solutions are at 25 degrees Celsius, you get to use your 1 times 10 to the negative 14th. And that's really what I would expect on the exam too. But just so it's like kind of you understand that KW can change and that the pH of water of like neutral water can change. I thought this was like kind of an interesting problem. And so it says that at body temperature at 37 degrees Celsius, Kw, instead of being 1 times 10 to the negative 14th, is 2.4 times 10 to the negative 14th. But as long as you remember that Kw equals the concentration of OH minus times the concentration of H3O plus, and that they're going to be equal in a water solution, you'd have, which they will be if you're using Kw, you can just kind of create Kw equals x squared. And so you just square root this 2.4 times 10 to the negative 14th value in order to get the concentration of the H3O plus and the OH minus. And so in this case, x equals 1.5 times 10 to the negative 7th molar. So you just have to do, then you would know, okay, like x just stood for the OH minus and the H3O plus. So your H3O plus concentration is this 1.5 times 10 to the negative 7th molar. So you just plug in for pH like usual, and you would do pH equals log times or log of H3O plus. And so in this case, your pH would be 6.8. So like instead of being 7 for a neutral pH at body temperature, the pH is 6.8. How was that one? Did you guys have any questions about that one or anything? Or was that okay?
Just to reiterate, so did you just say that when it's pure water, the OH and the H3O are like equal?
Yeah, when it's
Always?
yeah.
So always like when it's pure water, that's the case, correct?
Yeah.
Okay.
So like but then like that's different if like when you have these concentrations where it's like you have H3O plus and OH minus, they change concentrations and like that's no longer just pure water. But when you have like just pure water, the concentrations are equal. That's why they're both for the 1 times 10 to the negative 14th, if you remember that number for Kw at 25 degrees Celsius.
Yeah.
Then your OH minus and your H3O plus are both 1 times 10 to the negative 7th, which is why if you took the log of that, the negative log of that, it would be 7, which is a neutral pH. So just kind of like
Got it.
value changes of Kw.
Okay.
How did
Thank you.
that? Yeah, of course. How was that for you guys, Kelly and Paula?
Makes sense.
Okay.
Yeah.
Okay. The next one was just finding the pH of a solution that had a concentration of 0.052 molar in HBr and 0.020 molar in HNO3. Are these acids, are they both strong? Is one of them weak, or are they both weak? What's the deal with HBr and HNO3?
HBr is strong, correct?
Mm-hmm. And do you remember HNO3?
Weak.
That one's actually strong. I know it's kind of a weird one because it has the nitrogen in there, but it's actually a strong acid. So they're both strong, which actually makes the problem like a little bit easier. And so if you remember, strong acids dissociate completely. So you don't have to do any Ka expression or anything like that. You just have to add the concentrations, because the concentration of a strong acid is the concentration of H3O plus because they dissolve completely. You have to add the concentrations of HBr and HNO3 in order to get your total concentration of H3O plus. And so your H3O plus concentration in this case is 0.052 molar plus 0.020 molar, and you get 0.072 molar as your total concentration of H3O plus. And then you have to take negative log of that value, so you get a pH of 1.1. Do you guys have any questions about that one?
I have one question.
Yeah.
So I didn't even know you had to do math. I kind of just thought, okay, since they're both strong acids and I knew that they would dissociate completely, like that would mean that they would have like the lowest pH, and that's how I chose 1.1. Like, was that a safe assumption as well, or like no, like that's not always the case and you would have to do the math?
I think you have to do like it was a good idea in this case, but I think that if I had made one, like I could have made an answer choice that was like 0.9, you know what I mean? So I guess like it was definitely a good assumption that it would be a really low pH, but I think you have to still do math to find like the exact pH.
Okay.
How would saltiness change if it was a strong acid and then a weak acid?
I think that we do. I think I have an example of that. Yeah, so number 8 has a weak acid and a strong acid. So we'll go over that in a sec, but the idea is like you have to also use the Ka to find how much H3O plus the weak acid produces, instead of just like being able to add them together.
Oh, okay. Oh, I think I actually did that. All right.
Okay.
Thank you.
So yeah, well, so we're on number 6 right now, so we'll get to that one in like a few questions. I'll let you know. So for number 7, we have determine the percent ionization of a 0.225 molar solution of benzoic acid, and you have a Ka value of 6.5 times 10 to the -5. And so if you remember for your weak acids, the reaction they go through, and I don't really remember the formula for benzoic acid, but I'm just going to write Ba for benzoic acid. You'd have benzoic acid reacting with water. And if you remember, the water is a liquid, but your benzoic acid would be aqueous. And then if you went to, if they reacted, so if you put the benzoic acid in a water solution, then you would end up creating H3O plus, because it's benzoic acid, so I can write it as HBA. And so I'll write it as HB so that I can write the conjugate base. So you end up getting H3O plus because this proton would leave the benzoic acid and join the water, and then you'd also get the conjugate base, which would be like the benzoic acid, like I don't really remember what benzoic acid the formula it looks like, but it would be like the non-H part, it would be that and have a negative charge. So we write it as B- in this case. And so the important thing to consider here is that you would need to include in your equilibrium expression, you would need to include your benzoic acid concentration, your H3O plus, and then your conjugate base. But you don't include water because water is a liquid. And if you remember from last chapter, liquids and solids do not get included into your Ka expressions, only aqueous or gases, but you're not going to encounter gases, and acids and bases get included in your equilibrium expressions. And so for this, it would be Ka equals H3O plus times A minus over HA. And I think that instead of like having to create an ice table each time, if you guys don't have like this formula memorized or written down somewhere, it might be easier to like do these kinds of problems quicker during your exam instead of having to like make an ice table each time for weak acids. And so the idea that you have to remember with this is that if you actually drew out an ice table for it, you'd have their initial concentrations, you'd have their change in concentrations, I'm going to write as a delta sign, and then you would have your equilibrium values. And so if you remember, like however much, in this case it's 0.225 molar, and you start off with 0 H3O plus and 0 of your conjugate base, if you remember, like however much you're taking away from your acid, you're going to produce an H3O plus because you're going to get, for each amount of your benzoic acid that you're using, you're taking a proton away from each mole of that you're using. So you're going to get, however much you're subtracting, you're going to get that produced in H3O plus, and you're going to get that produced in your conjugate base because your benzoic acid is just splitting essentially into a proton and into the conjugate base. And so you'd end up having your 0.225 molar minus X, and then you'd have X for your concentration of H3O plus and X for your conjugate base. And if you remember your, usually you'd have to do like to make your small X approximation to make sure it's okay. But right now we're already solving for percent ionization, so we'll already check to see if it's, to see if the small X approximation is okay. So we're going to start off using it and see if it's okay or not. And so we have our equilibrium expression as H3O plus times A minus, and A minus is just our conjugate base over our weak acid initial concentration. And so we can use this small X approximation and just make it X squared over HA. And so we make it X squared over 0.225, and we set it equal to our Ka, which is 6.5 times 10 to the -5. And so you have to multiply that Ka value by 0.225, and then you would square root it, so you get an X value of 0.00382. And then for percent ionization, you just do your concentration of H3O plus over the initial concentration of your weak acid. So you do 0.00382 molar over 0.225 molar, multiply by 100, and you get 1.7%. And then, or yeah, 1.70%. And you also know that your small x approximation is okay because it's less than 5%. Do you guys have any questions about this one at all? Was this all right, solving for and everything?
It makes sense to me.
Yeah, I got it.
Awesome. Okay, so then we'll go to the next one. Okay, so we have a 0.148 molar solution of a monoprotic acid has a percent ionization of 1.55%, and then you want to determine the Ka value. So it's kind of like the inverse of this, where you were solving for the ionization, the percent ionization. Now you're trying to solve for the Ka, and in this case you had the Ka. You're like doing the reverse of it, where now you have the percent ionization, but you want to solve for the Ka value. So it's kind of like the exact opposite of the way that you just tackled this problem. If you remember that percent ionization is the concentration of H3O plus over your initial concentration, you can use your initial concentration and your percent ionization in order to find your H3O plus concentration. And so if you do that, you would end up taking this 1.55%, you would divide it by 100 because you multiply by 100 to get the percentage. And then you'd also multiply by this 0.148 value, which is the initial molarity of your weak acid. And then you would get the concentration of H3O plus, which is 0.00229 molar. And so because the percent ionization, which we were given is 1.55, is less than 5%, we can just use the small x approximation in our calculation for Ka. And so we do Ka equals H3O plus times A minus over HA. And again, like this is just your conjugate base, this is your weak acid, and you can use this little expression for, like that'll always be true for weak acid dissociation and figuring out like how much H3O plus would be produced by a weak acid dissolving in water. And so you would get your Ka equals x squared because you're using your small x approximation over your HA concentration without having to do the minus x because you know the small x approximation is valid. And so you just do your Ka is equal to 0.00229, which is your concentration of H3O plus squared over 0.148, which is your initial concentration of your weak acid. And then you would get your Ka value to be 3.56 times 10 to the negative fifth. So this one. You guys have any questions about that one or anything like that? Or like any of the steps to get there? Was it okay? Does it make sense?
Makes sense.
Yeah, it makes sense. I like messed up because I didn't actually like square the 0.00229.
Oh no, you got that far and you just forgot to square it.
Yeah.
That's at least really close. I think the hardest part is knowing to solve for the H3O plus like this way. So yeah, really close. All right. Okay, so now this kind of goes back when Bryce asked like that great question of like, what do you do if you have a weak acid plus a strong acid? How do you find the pH of that solution? This is an example of it because we have HBr here, which is a strong acid, right? But then we have HCH02, which is a weak acid. And so we're given the Ka value for HCH02, which is formic acid. So we have the Ka value for it, and we have to figure out what the pH is. And so the first thing you can do is like, you're gonna put the HBr into your solution. It's going to dissolve completely. And so the concentration of HBr is the concentration of H3O plus. And so the concentration of H3O plus contributed from HBr is 0.115 molar. So now I have to figure out how much H3O plus is actually being contributed to the solution by the formic acid, the HCH02. And so it's the same thing we were just talking about, where you can do Ka equals H3O plus times A minus, which is your conjugate base, over the initial concentration of your weak acid. So you just do that exact same thing again, but the only thing that you have to consider here is that you no longer have, like, you know how in the past we had done like x squared, you just done x times x. Well, now you actually have H3O plus present in the solution as well. So instead of doing x squared, you have to do 0.115, which is your concentration of H3O plus contributed by the HBr, times your x, which would be your A minus, your conjugate base, over 0.125, which is the concentration of the formic acid. So it's kind of the tricky step of doing it for the weak acid here. And so when you actually solve for this, you have to solve by multiplying 0.125 over and then dividing by 0.115. And so you get an x value of 1.96 times 10 to the negative fourth. And so just to check to make sure that the small x approximation was okay to use. And so you would do 1.96 times the negative fourth over 1.25, and you would get a concentration of we would do multiply by 100, and you would get 0.157. And so even though you didn't have to do the small x approximation here, so there's not going to be any additional there's not going to be any additional H3O plus that's added that's like so large that you have to include it in your Ka expression. But if you did, it would be 0.115 or plus x, because your x value is going to be the same one. Like, it's how much, if your weak acid is dissolving, that's how much is going to be added. And so if you were to add on your x, and it would, like, if it was not just a small x approximation, you could add on that plus x to the 0.115. But it's such a small value, like it's so small, it's 1.96 times the negative fourth, that when you add it to the initial concentration that HBr contributed to the solution, it like doesn't make a difference with sig figs. It just stays as 0.115. And so your pH just becomes negative log of that 0.115 value. Sorry, I wrote log, but it should be negative log of that 0.115 molar value. And so you get a pH of pH of 0.939. Does that make sense? Do you have any questions about that? Basically, like, you did this problem to try to see how much like x you were creating, like how much of x, how much of the H3O plus you were adding into the solution here, but it was so insignificant in comparison to how much the strong acid contributed that you ended up just using the strong acid to find the pH anyway. Does that make sense? They should take it on like a case-by-case basis. It was just, in this case, the acid the H3O plus that would be contributed was so small that you could just use your small x approximation and it wouldn't make a difference.
For when you added like the 0.115 plus 1.96 times 10 to the negative 4, wait, why'd you have to do that again?
So, okay, so I was kind of showing here. So if you're able to do your small x approximation, so okay, so I guess like first, like your Ka value will be set equal to your H3O plus, which is like how much H3O plus is already in the solution from your HBr, plus x, which would be the H3O plus that was contributed to the solution from your Ka or from your weak acid. So usually that would be like if you just did a standard Ka, like Ka approximation, it would just be H3O plus, which you could make make x, but because there's already some H3O plus in the solution, you have to kind of add that to x to how much H3O plus will be produced by your weak acid. And so because of small x approximation, we can kind of like just say like, okay, we're not going to include this plus x and we're not going to include this minus x, and then we're going to check percent ionization and then see if we can if it has to be included or not. And so when you solve for x, you get 1.96 times 10 to the negative fourth, which would be the value that would go here for the addition of H3O plus, and would go here for your conjugate base, like for your concentration of your conjugate base. And so you get that to be 1.96 times 10 to the negative fourth. And so if you do your percent ionization to check that your small x approximation was okay, you get 0.157, which is already such a small percentage of ionization. You could definitely use a small x approximation. So right there you could stop and you could say, if small x approximation is okay, then the H3O plus didn't even need to be added to this other value that I solved for. So it must only be the H3O plus that impacts pH. But if you wanted to just like be sure and really like prove to yourself that the H3O plus didn't contribute to anything, you could do your H3O plus equals 0.115 molar, which is the concentration contributed by your HBr, plus the concentration that would be contributed by your weak acid, your formic acid. And if you were to try to add those two things up, because this value is so small with sig figs, it wouldn't even, like it wouldn't contribute. So it doesn't matter. Yeah. Does that make sense?
Yeah, does.
Okay. Do any of you other guys have any questions about it? Or does that make sense?
No, it doesn't make sense. Sorry. I was just saying that I gonna have an emergency. So I'm gonna have to go. But I'll come back. Can I stay on?
Yeah.
I just want to say I just have to leave right now, but I'll be back in like 20 minutes.
Okay, sounds good.
Thank you.
So, okay. So for the next problem, Kelly, are you good too on that one?
Yes.
Okay, awesome. So for the next one here, we have to determine the pH. Sorry, so this is 0.939. Okay, so then the next one we have to determine the pH of a solution, and we're given the mass, the percent mass of KOH. And we're given the density of the solution. So if you remember, I think we did like a similar one to this last week, but I think it was maybe with an acid. So KOH is a strong base, so it's going to dissociate completely. And so we don't have to worry about doing a KB expression or anything here. We just have to get the concentration of KOH so we can figure out what the concentration of OH minus is and then use that to find the pH. And so we do the important part for percent by mass, or yeah, for percent, or like weight by mass or percent mass is that oh my god, weight percent, that's what's called. For weight percent is that it's you just need to keep the ratio of the mass of that one substance in comparison to the rest of the substance. And so you could just say, okay, if I have 3.85 grams of this, I'm going to have 100 grams of solution just to keep that 3.85 percentage like the same. And so then you could go from there to try to get it into moles per liter of solution, so you have it in concentration. So in order to get into moles per liter of KOH, of the KOH concentration, you just have to do you have to multiply your grams of your solution by the density to get it into milliliters of solution. And if you remember, molarity is in moles over liters, so you have to just convert milliliters into liters. And then the last step is just to get the grams of KOH into moles of KOH. So you should come away with 0.693 molarity of KOH. Do you guys have any questions about that at all? How I solved for that first? Or does that make sense? Were you able to do that and everything?
Yeah.
Okay.
Do it.
So then if you have that, the next step is to figure out, there's either two ways you could do this. I chose to do like POH calculation. So your POH is just your negative log of your OH minus concentration. And that's what I did. So because KOH dissociates 100%, it's just the concentration of OH minus as well. And so you used to do negative log of 0.693 molar, and you get a POH of 0.159. The other thing you could do instead is that if you know that KOH is going to dissociate 100%, you could go back to that autoionization of water equation and like find your concentration of H3O plus ions. I just think it's easier to work with like without having to use the super small numbers. So after you find the POH, remember that I asked for pH. So the last step that you have to do is just, if you remember pH plus POH equals 14, you just have to do 14 minus the POH in order to get pH. So in this case, you do 14 minus 0.159, and you get a pH of 13.842. And you can kind of check yourself on that by saying like the KOH is a really strong base. It should be a really high pH because it's really basic. So that would at least hopefully rule out these three options for you. Do you guys have any questions about that one? Were you able to get that and everything? Do you have any questions?
All good.
All good? Awesome. Okay, so for the next one here, it's looking at salts to see if they're going to form solutions that are like basic, acidic, or neutral. And so this again goes back to knowing if your acids and your bases are strong or weak, depending on which ion you have. And so the reason for that is, like, again, if you have a super strong acid or base, it's going to dissociate completely, and it's totally okay. Like that anion, if it's a strong acid, like HCl, for example, if you dissociate HCl, Cl minus is so electronegative, it can hold onto that negative charge. It's super stable. It already dissociated 100%. So then why would it like try to glob back onto an H plus? So things like that. Like, so if you have, if you had a really strong acid, then your pH, then your conjugate is going to be pH neutral. If you have a weak one, a weak acid or a weak base, your conjugate will be stronger, because a stronger acid or a stronger base, because it needs that proton or that other compound to be stable. And so, for example, for AlNO3,3, if you remember how HNO3 was one of your strong acids, that means that NO3 is like the worst base ever, because it's totally stable without having to have a proton on there. And so NO3 is going to be pH neutral, but Al would be the conjugate base of that would be Al OH3, which is a weak base. And so because of that, if you have a weak base, then the conjugate acid, which would be Al3 plus, is going to be a strong, like not a strong acid, but it will be like stronger. And so it's going to be acidic. But RBI, for example, RBI would be, you'd have HI as your conjugate. HI would be your conjugate acid, which, if you remember, is strong. So it's going to dissociate 100%. And I minus is totally happy just hanging out without a proton. And RB would be RbOH. And RbOH is one of the strong bases. And so that would be neutral because both of these are strong. So their conjugates, the I minus and the Rb plus, are totally okay with just hanging out in the solution. Then you have FeI3, which is really similar to A. You have FeOH3, which is a weak base. But you have HI would be your strong acid. And so since HI is a strong acid, the I minus will be pH neutral, but your Fe3 plus is going to be acidic. And so C would be acidic. Then you have a similar idea for D, where you have the C2, H5, and H3 bonded to, that'd be plus, bonded to NO3. And NO3 is part of a strong, or NO3 minus. NO3 minus, the conjugate of that would be HNO3, which is a strong acid. So HNO3 is going to be it's going to be the weakest base in the world. It wouldn't even be basic, it would just be pH neutral. But the C2H5NH3 is not a strong acid, and it's the conjugate of C2H5. That's an H, sorry, the worst H ever. C2H5 and H2, which I think you guys had to use this compound in a problem for recitation. This is a weak base, and so if it's a weak base, then its conjugate is going to be a stronger acid, and so the solution will be acidic. I just want to be clear when I talk about these, like, even though they're stronger, or it's like a stronger acid or base, like these are not like how there are strong acids and strong bases. They're just like relatively strong or weak in comparison to the other conjugates. There's a list of like designated strong acids and bases that like you can kind of remember or write down if they're in your textbook to know for the exam. NAF, you'd have Na would be part of NaOH, which is a strong base. And then you'd have HF, and if you remember, HF is a weak acid. So HF you'd have F minus would be a base that would still want to have this H because it's more stable with the H, and it doesn't dissociate 100%, but the NaOH is going to dissociate completely, and that OH, or the Na is like totally content being in the solution as Na plus. And so that the Na ion is just neutral, but the F minus ion is basic. And so E would be basic. And then finally for the last one, NaOH again, strong base, it's going to be pH neutral for Na plus. HBr is the conjugate of Br minus, and that's a strong acid. So Br is totally content being in the solution by itself. And so the solution overall would be pH neutral. Do you guys have any questions about this one? I know it's kind of weird to think about. It's kind of hard sometimes to think about the salts and to think about like the different ions being acidic or basic when they're not necessarily what you think of as like an acid or a base. Do you have any questions about that one?
Yeah, I have a question. So for NaF, it's basic because the Na is a spectator of the OH.
Yeah, that's a good way to put it. Yeah, that's the Na is a spectator of the OH, and it's not going to be like the Na is like, because the NaOH dissociates completely, the Na plus is like totally content having that positive charge in the solution and is not going to try to bond to an OH minus. But the F minus is still part of the HF, which is a weak acid. So it won't dissociate all the way. It's not a spectator. And so you end up having a basic solution. Yeah, that's a good way to think of it too with the spectators, I think.
Okay, and then can you just go over number 4, please? I'm sorry.
No, yeah, of course. So I think it's so hard to think about because it's a big one. But the way it would break up would be right here. And so you'd have NO3 minus, and you'd have C2, H5, and H3 plus. And I think that potentially you guys had to work on this, like with this compound in recitation like a week ago. So your NO3 minus, the conjugate of that is HNO3, which is one of your strong acids. There's just a list of strong acids. And right now I'm working on like making a little like 1-page review sheet that has like the strong acids and bases on there. So I'll try to post that tonight. But it's just like one of your strong acids. So that one will be pH neutral because it dissociates all the way. So the NO3 is going to be neutral. So it really depends on what this like weird compound is going to be. And so C2H5 NH3 is a weak acid. And so the solution is going to be acidic. But the other way to think of it too would be that the conjugate of it would be C2H5 NH2, which is a weak base. I think that's what you were given in recitation the one day when you had to do the problem. And where it was like C3 or CH3, something like it was one of those kinds of one of these kinds of like bases. This is just a weak base though, and so because this is a weak acid, it would make the solution acidic. Does that make sense?
Yeah, that makes a lot of sense. Thank you.
Okay. So this next problem was arranging the solution in order of increasing acidity. Sorry if there's like 2 blank options here. Sometimes the quizzes on Canvas when I make them, sometimes it's just like it just makes like random things happen that I don't understand, like why I included 2 blank answers. But anyhow, arrange these solutions in order of increasing acidity. So the first thing you can immediately be like, okay, this is definitely on the like lower end of everything, would be your NaOH because it's a strong base. So it's going to be like a super, super, super low, super low concentration of H3O plus. It's going to be really, really basic. So that has like a very, very, very low, like it's not acidic at all. Super low, it would be the lowest on your list. The next thing to consider would be, okay, do I have any others that are basic? And so NaHCO3 is kind of a weird one, but it would dissolve into Na plus, which is pH neutral, but it would give you HCO3 minus, which is actually a base. So there's a list of other bases. If you remember, H2CO3 is an acid, is a weak acid. And then its conjugate base is HCO3 minus. And so then that would be basic as well. And so that would be your next in line, because a strong base is going to be more basic than a weak base, but the weak base is still going to be basic. And so now you can check, okay, do I have any other bases? So you can cross out, oops, I need to cross out the NaCl. You can cross out your NaOH, you can cross out NaHCl3. But none of these other guys are basic. Like the rest of them are all acidic. And so you would have, you'd next have NaCl, because NaCl is completely neutral, because NaOH is a strong base, it's going to dissociate all the way. Na plus is not going to contribute, and then HCl dissociates all the way. Cl is a spectator ion. It'll be completely neutral, and so you would have NaCl right like smack in the middle. And then you have NH4ClO2. And if you remember, NH4 is a weak acid, because it'll be NH4 plus. So that'll be more. So even though you have the ClO2 contributing here, you have like the ClO2 contributing, which will bring down the pH a little bit, because this is a weak base, because HClO2 is a weak acid. Even though you have that bring in, because you have the NH4 plus, it's still going to be a higher pH than like a neutral solution, and higher than your basic solutions, because it does have that acid present, but it won't be the highest. And then your last one would be NH4Cl, because the Cl is only a spectator ion, so the one that would be contributing to the solution would be the NH4 plus, and so because of that, NH4Cl is your most acidic in the bunch. Do you guys have any questions about that one? So it'd be this one. Any questions about, I'm sorry, that one. Any questions about that, or is that all good?
That makes sense.
Okay,
Yeah, makes sense.
awesome. Okay, the next one you have is a formic acid solution, has a pH of 3.25, and then it says, okay, which of these substances is going to raise the pH of the solution upon addition? And so we can go through each of these. So if you add HCl, you're going to be adding in more H3O plus, right? And so that's going to decrease your pH, because the lower the pH, the more acidic it is. So A is actually going to decrease your pH, so it won't be that one. NaBr is completely neutral, right? These are both spectator ions. NaOH is a strong base, HBr is a strong acid. They're both just like hang out in the solution. They don't need to glob on to the H3O plus or the OH minus. They're just gonna like hang out in the solution and do nothing. And so they're not gonna contribute at all. And if we go down to D, it's the exact same thing. KOH is a strong base, HCl is a strong acid. They're both spectators. They're not gonna contribute to pH at all. They're just gonna like hang out in the solution and not do anything. So now we have to just go to this one here, which is NaCHO2. And so this will dissolve into Na plus, which is a spectator ion. It's NaOH. It's a super weak base. It wouldn't contribute to pH. Or sorry, super weak acid. It wouldn't contribute to pH at all. But we have CHO2 minus. And formic acid is actually CHO2, which is what we I think was used like in an earlier expression or an earlier question as well. So formic acid is this HCHO2. And so you have its conjugate base right here. If you have a base in the solution and it already has a weak acid as a, as if it's the conjugate of a weak acid, then it's going to be like a strong-ish conjugate base. And so because of that, if it's basic, it's going to increase the pH of your solution, because it'll make it more basic. And so C is the answer to that. Do you have any questions about that one at all? Okay. All right, for the next one here, we are starting to move into buffers. And so if you recall, the whole idea of buffers, just want to go over it again because I feel like buffers are still like a confusing idea to a lot of people. The whole point of a buffer is that you have two substances. You have a weak acid and your conjugate base, or you have a weak base and its conjugate acid. And the whole point of it is that no matter what you're adding into the solution, if you're adding a base or an acid, there's going to be some kind of a species in the solution that is able to to bond with that acid or base added and make it neutral and neutralize it, so the pH doesn't change so much. And so the idea is like, okay, you have CH3 NH2, which is a weak base, and you can know that because you're given a Kb value for CH3NH2, and also because there's like a list of common weak bases that in your textbook that might be useful to have. I know that you might think, oh, it has an H attached to an N on it, it's okay to use, but it's still a weak base because you can actually bond another H onto this nitrogen here. And you can kind of see that too if you look at the other compound that you're working with. It's CH3 NH3 plus, because it's going to dissolve away from that Cl. So hopefully if you had those two together, you're able to recognize, okay, if I'm given the Kb for this and its conjugate is positive and has an extra H, then this is the base and this is the conjugate acid. And so the idea for it is that when you have a buffer is that if you are adding an acid, you have a base that can react with the acid. And so if you add like HBr, you get H3O plus, so you have HBr, it would go into the water, it would give you H3O plus. Actually, I don't know why I do the double arrows, it'll dissociate completely. So it'll dissociate 100%. You'll get H3O plus and you'll get Br minus, and Br minus is just a spectator. And then after, in all these solutions, they're all aqueous and water is present in all of them. So if you ever get HBr, you can just start thinking of it as H3O plus because it's going to dissolve and react with the water. And so if you have HBr and it reacts and produces H3O plus, then you're going to produce, after you produce H3O plus and HBr, you'd have the H3O plus react with the weak base, which in this case is CH3 and H2. And you would end up creating your weak acid, CH3, NH3, which is already present in the solution, and water. And because water is neutral, it doesn't contribute to pH, and you already have your conjugate acid present, so it won't change the pH like crazy. The opposite thing would happen if you added a base in, it would take this weak acid and it would end up making it into the conjugate base and into water again. And so that's how the buffer works, where like essentially if you add an acid, the weak base is able to react with it. If you add in a weak acid, or if you add in an acid, if you add in an acid, the base can react with it. If you add in a strong base, the weak acid can react with it, the conjugate acid in this case. So that's just kind of buffers generally, but for this expression, it's not asking you to add anything in yet, it's just asking you what the pH is of a buffered solution. And so because the concentration of CH3 and H2 and CH3 and H3 plus are really similar, they're the exact same in this case, we can use the Henderson-Hasselbalch equation for it. The only thing that we have to do first is that we're given a Kb value. And so we need to solve for our Ka. And so we go back, remember your Kw is equal to your Ka times your Kb. And so in order to solve for your Ka, you would just do Kw divided by Kb. And so if you remember, your Kw is 1 times 10 to the negative 14th, and you would get your Ka value to be 2.3 times 10 to the negative 11th. And then you can go back to your Henderson-Hasselbalch, which is pKa. Remember, pKa just means negative log of your Ka value. The same way like pH is negative log of your H3O plus concentration, that P just means you negative log it. And you have to do your weak or your conjugate base over your weak acid. So just make sure that you're doing, in this case, it doesn't really matter because they're the same, but make sure that you would plug in the correct things. This would be your conjugate acid, so that would go in the bottom, and this would be your conjugate base, so it would go in your numerator. So you do 0.18 over 0.18, and you get a pH of 10.6. So it'd be 10.6. Any questions about that one at all? Or about buffers in general before I move forward with a bunch more buffer questions? Are you guys feeling a little bit more comfortable with the concept of buffers now, like this week as opposed to last week, or are they still feeling really confusing?
They make more sense.
Making more sense? That's good.
Yeah.
Okay, for this next one, we have calculate the pH of a solution that results from the mixture of 235 milliliters of 0.1 NH3, and then you also have 0.10 NH4Cl, which will resolve into NH4 plus, which is your conjugate acid. And so you're given like milliliters and moles of both of them, but the first thing you have to do is convert into, so you're given milliliters and molarity, but in order to actually be comparing these guys, you need to be able to have the number of moles of each of them. And so you can find new concentrations for them because they're being mixed together. And so if you do, so instead you can't just like plug in these concentrations because you're mixing two solutions together. So you need like their new concentrations. And so if you do I did 235 times the concentration of NH3, you get 0.0235 moles of NH3. And if you did 250 milliliters of your concentration of NH3, you would get your concentration of NH4 plus. You would then get 0.250 moles of NH4 plus. And so the last step you have to do before you plug into Henderson-Hasselbalch, just like last time, is that you're given a KB and you need your Ka. And so you just do the Kw divided by Kb to get Ka. So you do 1 times 10 to the negative 14th divided by 1.76 times 10 to the negative 5th. You get a new Ka value of 5.68 times 10 to the negative 10th. You just plug it into Henderson-Hasselbalch and just make sure that you do your conjugate acid goes in the denominator and your conjugate base, or your weak base, goes in the numerator. And overall, the pH is 9.22. Yeah, the pH is 9.22. You guys have any questions about that? Okay, so we can kind of keep talking about buffers and kind of go into like a more abstract idea of a buffer without having to actually really do like any real calculation here. For this one, you have to just look at each of these and figure out whether or not a buffer really resulted in. And so you have NH3 and NH4Cl. And so if you remember a conjugate, or sorry, if you remember a buffer has to either be a conjugate, either a weak acid and its conjugate base, or a weak base and its conjugate acid. And so in this case, you have a weak base, and then its conjugate acid is NH4Cl, or yeah, is NH4 plus, which is supplied to you by NH4Cl. And then because you have this like really similar amounts of both of them, it's going to be a buffer. And so A would be a buffer, and then you have B is a strong acid plus a strong base. That's not going to be a buffer because you would just have you just pour in these two, and then it would just the Cl would just be a spectator, and the Na plus would just be a spectator, and then the this H and the OH are going to end up just bonding and then producing H2O and just being neutral, and they won't be able to actually support like any addition of anything else in. And so B is not a buffer. And if we can, I'm gonna wait 1 second to go back to actually, okay, so for the last three here, you have to consider are any of these a buffer. And so each of them has a weak, so actually this one has a weak acid, and this one these both have weak bases. And so for the weak base ones, you wouldn't have a buffer because you would be adding a strong base to a weak base, which wouldn't have anything to react with the acid. And so neither of these are buffers. But this one, you may have initially thought, oh, that's not a buffer because you have HF, which is a weak acid, and you have NaOH, which is a strong acid. I don't see its conjugate base anywhere. So that wouldn't be a buffer. But because you have 50 milliliters of 0.15 molar HF, and you have less than that of the NaOH, what actually happens is that you have the HF react with the OH minus, from the NaH, and then what happens is that the H is going to leave the HF in order to stabilize the OH minus, and it's going to create H2O plus F minus. So it actually ends up creating your conjugate base. And so because it actually ends up creating your conjugate base, you actually have your acid and then the conjugate base that your NaOH created. So the important thing to consider here, if you ever have another situation like this, is that it's really important that there's more of the weak acid than there is of the conjugate, or of the weak base, or sorry, of the strong base, because if there was like a strong base added in and it was like 100 milliliters of NaOH, it's going to neutralize all of the HF, and then you're just gonna have a really basic solution. But because in this case, it's only like half of what was supplied by the HF, it'll just like neutralize like half of the HF, not all of it. So you would have a buffer. Does that make sense?
Wait, so you're saying that you need more of the strong base, correct?
You know, you need more of the weak acid, because if you had more of the, okay, so like right now you have 50 times 150. Right now you have 7.5 moles of, oh wait, sorry, 0.05 times. Right now you have 0.0075 moles of HF. So if we have HF, we have 0.0075 moles. And it's going to react with the NaOH, that's a 5, NaOH. And currently we have, if you do 0.02 times 0.15, you'd have 0.003 OH. And so that's going to form H2O, and it's going to form F minus. And these are both 0 right now. So what actually happens is that because the NaOH is the limiting factor here, you do minus 0.003, and then you do minus 0.003, and you would still end up having 0.0045 moles of HF left. Sorry, that's a 4.045. And then you would actually add on this value to the water and to the F, but the water doesn't really matter. But you'd add it to the F, so you'd have 0.003 moles. So in this case, now you have your conjugate acid and your conjugate base present. If you had so much NaOH, like let's say that instead of having 0.003 moles, okay, so I guess, so right now we have a buffer because we have F minus present, which is the conjugate base of HF, and they're present in similar amounts, so it'll be a buffer. But if instead of having 0.003 NaOH, we had like we had 1 mole, we had like 1 mole, or like maybe I'll say like we had 0.85, because that'll just be easier for math. 0.85 moles of NaOH. If you had more of the NaOH than you did of the conjugate acid, then you'd end up actually having the, instead of being able to like subtract it like this and still getting some HF, the conjugate acid would be the limiting factor. And so you have to do minus 0.75 for all of these. Minus 0.75, minus 0.75, and plus 0.75. And then now you would just have 0 of your strong acid, and then you'd have 0.001 of your strong acid, or your strong base, and then you have 0.0075 of your weak base. So it wouldn't be a it wouldn't be a buffer anymore, because you'd only have base present. You wouldn't have any acid present to neutralize. Does that make sense?
Yeah, that makes sense.
Okay. So so it would only be the 100 milliliter of NH3, H4, it'd be this one, and then this one. Okay, so for the next one, the next one was your initial pH of a solution, and then, or actually only after the addition of was afterwards, after adding 0.00 or 0.020 moles of HBr. So if you have this right here, you have a 100 milliliter buffer has 0.175 molarity of HClO and 0.150 molarity of NaClO, which will make ClO minus, which is the conjugate of HClO. And so before we can actually do our ice table, we need to have, oh my gosh, I don't know what happened to this. It's so 0, 2, 0. Because we have our ice table here. I don't know what happened to this ice table. 0, 2, 0. Because you have your HBr in terms of moles, you'd have to be adding, or you have to like have everything in moles in order to actually be able to like make the ice table and actually compare the two of them. And so you would have to convert your HClO and your ClO minus into moles first. So you would just take the concentrations and multiply by their volume to the number of moles, and just make sure that you have to convert into liters, because molarity is in liters. So you end up giving 0.175 moles of HClO and 0.0150 moles of ClO minus. And so you have to do, you'd end up doing minus 0.0020 moles, because you'd have 0.00 or 0.020 moles of H3O plus, which is your limiting. And so you would subtract 0.002 from this, and you would get 0.0, so 0.0175 minus 0.002, and that would be 0.0155 of ClO minus now. And then you would have your concentration of CH2 or CH3 plus would end up actually becoming 0, because it would all be neutralized, and it would create water as well, but you don't have to really consider the water, because the water is not going to be included in your equilibrium expression. And so you would do 0.015 times or plus 0.0020, and so you would get 0.015 plus 0.002, and you would get 0.017 moles. 0.0170 moles. And so this is all wrong. I don't know what happened here. You'd have to use your Henderson-Hasselbalch. So instead of doing, you'd have your Henderson-Hasselbalch and you have your Ka, you're given it as 2.9 times 10 to the negative 8. And so you have to do negative log of that, and then you would add, or you would have to do your conjugate base over your, or your conjugate, your conjugate base over your conjugate acid. And so you'd have 0.015 5 moles of your conjugate base, and you would have 0.07 or 0.0170 moles of your conjugate acid. And because they're going to get like in a ratio anyway, you wouldn't even have to worry about like including your volume in there, because it'll end up canceling, it'll end up like getting like canceling out anyway, even if you added the liters on there. So if you do negative log of 2.9 e to the negative 8, you would get 7.5. 7.54, and then you would have to do log of 0.0155 divided by log, or divided by 0.0170, and you would get negative 0.040. And so when you actually do your pH, you do 7.5 minus that, or plus that negative 0.04, and you would get an overall pH of about 7.50. And so the answer should actually be 7.50. So the answer for this one actually should be none of the above. But that wasn't purposeful. I just messed up. So the answer for this one is actually 7.5, and now it's fixed in the answer key. Do you guys have any questions about that one?
Yeah, so like when you're working with ice tables, are you working with the molarity or like the moles? I think that's always confused me because I think I just got lucky with it being like 1 liter, but every time, but like what are you working, like what units is it?
So it doesn't really, you can do it in moles or in molarity. It just has to be the same no matter what you're doing. Because like essentially it just is like keeping the ratio the same. So as long as like it doesn't matter as long as it's the same thing no matter what.
Oh, okay, all right. I was just making sure. All right, thank you.
It has to either be moles or molarity, but you could be either one. It's the same.
Got it.
But do you have any questions about solving it or anything? Bryce or Kelly, I think you guys are both still here. Any questions about any of that?
All good.
Okay.
Yeah, I think I'm good.
So if you're feeling pretty good about like buffers like that, then hopefully like titrations, it might be hard to like change your mindset on how you solve them, but like buffers are basically doing this, or not buffers, titrations are basically doing this at different points in the titration. So like as long as you can like think that through, it should be like you guys should be pretty prepared to handle titrations, and we just be like getting more comfortable and doing more practice with it. For this one, we have which buffer system is the best choice to create a buffer with a pH of 7.2. If you remember that buffers, they're actually most stable if you have equal concentrations of both the A- and the HA, because that way, if you add anything else to them, then the pH isn't going to change that much because they already are the same. So like if they change a little bit, the pH will like not change so much, but if it changes, if they're already different and you add in something and it makes it even more different, then the pH could change a bit more. So they're actually most stable when the concentration of your conjugate base is the same as your conjugate acid, or really, really similar, because this whole log will go to 0 and it'll end up just actually being pH equals pKa. And so when you have to choose which buffer is the best choice with a pH of 7.20, you would have to do you have to find which one is the closest, which pKa is the closest to the pH of the buffer. And so if you remember, pKa is just negative log of these values. And so you would choose D here because negative log of 2.9 times 10 to the negative 8th is the closest to the pH of, or to the pH of the buffer, which is 7.2. Do you have any questions on how, about that one or how to solve that one? Then we'll go on to this one, which is a 500 milliliter buffer. Solution is 0.100 molar in HNO2 and 0.15 molar in KNO2, which is its conjugate base. Which additions would exceed the buffer capacity or the capacity of the buffer to neutralize it? So this is a really good question because it makes you think about which reactions are happening depending on which species you're adding in. So if you're adding in NaOH, which species is it going to react with? HNO2 or KNO2 minus, or KNO2, which will then become NO2 minus? Which one is the NaOH going to react with? Will the NaOH react with the acid or with the base? It'll react with the acid, right? Because if you're adding a base, it's going to react with the acid because like acids and bases react with one another. Bases and bases don't really react with one another. So you have to consider like, okay, if I'm adding NaOH, if I'm adding KOH, it's going to react with the acid. If I'm adding HBr, HI, it's going to react with the conjugate base. Does that make sense to think about?
Can you explain one more time?
So like for each of these, you have to consider which species it's going to react with. And so, for example, here, it's given a buffer solution. So you have an acid and you have its conjugate base. If you're going to add a base in, it's going to react with the acid. So NaOH is going to react with the acid, which is HNO2. KOH is going to react with the acid, which is HNO2. But HBr is going to react with the base, not the acid. So it'll react with NO2 minus, and HI will also react with NO2 minus. Does that make sense?
Yeah, that makes sense.
Okay. And so we'd have to do, in order to figure out, again, if they're going to neutralize it or not, you have to see if the, so it talks about the capacity of the buffer to neutralize. When you have a buffer that's neutralizing, it takes the concentration of the acid or takes the acid and it reacts with the base and ends up creating water and the conjugate. But sometimes it's the concentration of the base or the acids added in is too large where it actually it uses up all of the acid and there's still some of that strong base left, which makes it just be like only that strong base is contributing at that point to the pH. And so it's basically asking you, does the moles of this exceed the number of moles of the species it's going to react with? And so we already said that NaOH is going to react with the acid, which is HNO2. And so you have to figure out the number of moles of that. So if you had 0.100 molar times 500 milliliters, it's going to be 0.05 moles of HNO2. And so anything greater than 0.05 is going to exceed the capacity to buffer, but anything less than that, that's the base, is going to be okay. So that means that A will be able to react and won't neutralize, or sorry, which ones will exceed? A is not going to exceed, but B is going to exceed. But then for the other ones, for NO2 minus, that's for the acid to react with, because this is the conjugate base, you would have a total number of moles of 0.150 molar times 0.500 liters, which is going to be 0.06 moles, 0.07 moles of NO2 minus. So anything that's greater than, any acid that's greater than 0.075 moles is going to neutralize, but neither of these concentrations is greater than 0.075 moles. And so neither of these will exceed the capacity of the buffer to neutralize. So only the 0.0600 moles of KOH, this one here, is going to exceed the capacity. Do you have any questions about that? Does that make sense? What are you thinking?
That makes sense, but I didn't know how to do it before.
Okay, that's okay as long as you know how to do it now. Does it make sense to you, Kelly?
Yeah, a little bit. I just gotta I guess process it more later on.
Yeah.
Completely understand.
Definitely let me know if you have any questions about it later, if you look at it later. Because no, it's like a weird, I think it's kind of hard to think about, especially like which species is going to react, which species are not going to react. Okay, we're almost done now. So we have 2 graphs and we have two titration curves, and they are equal volumes of monoprotic acid, and one is weak and one is strong. And it's carried out with the same concentration of strong base. So it's basically everything is the same, except one strong and one is weak. So we have 2 things to figure out: what the pH is at the equivalence point of each, and which graph corresponds to the titration of a strong acid versus a weak acid. So I guess first, do you guys remember where the equivalence points happens on these kinds of, or on titration curves? Any like memory of where it happens? Or like any guesses for the equivalence point of where it happens?
Is that where like the like where the 12, like the pH 12? Is that where it's at?
It's actually that's like beyond the equivalence point.
Oh, it's PK.
The equivalence point is like right at the halfway point. It's when the moles of your acid equal the moles of your base. And so it's right halfway. And so that's not a great drawing here. And so it's right halfway. And so if you look like halfway between this and this, it's probably like right around here. And then you can go over to the pH here, and it's right around a pH of 8. And so for A, the pH is 8, but this one goes down a little bit further. So this one is like halfway, it's probably like around here. And so that one is closer to right around 7. And so the answer for the equivalence point of A would be 8, and the equivalence point of B would be 7. Do you have any questions about that one first? That part of it first.
No, that makes sense.
Okay. And then for which one corresponds to the weak acid and which one corresponds to the strong acid, I think there's two major clues here. The first clue is the pH, the starting point pH. This one has this like greater starting point pH, which means it is like a good indicator that it's going to be weak. The other thing that's good about this one, or that indicates that it's going to be a weak acid, is that the pH is above 7 at the equivalence point. Remember, if you remember, like a pH of neutral water is going to be exactly 7, and so a pH of a strong acid plus a strong base, you create a strong acid, HCl, plus a strong base, NaOH. You're just going to create water and salt. You're going to have Na and Cl are going to be spectator ions, and you're just going to create water. And so the pH when these two values are equal is going to be that of the pH of pure water, which is 7. So it makes sense that this one has a pH right at 7 because it's both strong acids and because the pH is really low in the beginning. And then the other thing to look at is that you can kind of see it in like this section of the graph. For strong base, strong acid concentrations, there's not really like a real like buffer area here. These lines are like pretty like they're kind of like shaped like this, as opposed to like being like a buffer and like slowly increasing in pH. And so that's the difference, where you can kind of see like this little like slow increase in pH because it's buffering there. Do you guys have any comments or any questions about any of that? So A would be to the weak acid and B would be to the strong acid. I think the easiest way to look at it is 7 pH is going to be a strong acid. Sorry, go ahead.
It just doesn't seem like that drastic of a difference for some reason.
No, I get that. It doesn't seem that drastic a difference. And
so like when I'm looking, I guess when you see like that, I guess it's like a really like serious change in the B rather than an A. It's like slow, so I guess you just have to look at that.
Yeah, I think that you can also like this. I guess the other thing that might be easier too is like how. First, I think the easy thing is like, okay, clearly the starting pH of B is a lot lower than that of A. I do think it's kind of hard to see that like this is at 8 and this is at 7, to like really pick an exact equivalence point. But the other easier thing might be like if you see how much longer this jump is, like as opposed to this short jump, because it wasn't buffering, the jump is like so much larger in the like strong as opposed to like the weak strong. Does that make sense? Like this line where it jumps from being.
Yeah, that makes sense.
Yeah. Okay. So then this next one, we have a buffer that is 0.100 molar in NH4Cl and 0.100 molar in NH3. And so I was asking if we add HBr to it, which buffer component neutralizes the added acid? So, okay, so we know, so the NH4 plus, because it's going to dissolve into NH4 plus and Cl minus, is the NH4 plus the weak acid or the weak base?
Is it the weak acid?
Yeah, exactly. So I'm gonna put an A, and then there's the NH3. Is that the acid or the base then?
Oh, the base.
Exactly. And so if you're gonna add in hydrobromic acid, it's an acid. So is HBr going to react with NH4 plus, which is the acid, or will it react with NH3, which is the base?
The base?
Exactly. So it'll react with NH3. So the answer for this one is NH3. Okay. So that was the whole exam. Before we do anything else, do you have any questions about any of the anything that we went over on the exam?
Can we just go over the question 20 again, like the graph?
Yeah, of course.
I'm not getting it.
So the equivalence point, if you remember, I know you just learned titration, so it's totally okay if you don't remember. The equivalence point is where the concentration of your acid and your base are equal. And so at that point, it's going to be like the exact halfway point in your graph. And so if you see this like really big jump here, that indicates that the equivalence point is happening. And so and here, as you see, if you like just look at the graph, you ignore the pH on the side here. You try to like look at this line on the side or in the middle here, and you're like, okay, where's the halfway point here? Let me put it like around like here. It's like the exact middle point. And so that's exactly where your the concentration of your or the number of moles of your acid equals the number of moles of your base. And so they should be like completely equal to one another. And so at that point, you have to just go over and look at the pH there. And so here is a pH of 8. Here, on the other hand, if you go right in between here and you kind of ignore the pH on the side and you just like look at it, don't think too hard about it, and like, okay, where is the halfway point between this like big line right here? You probably put it like right like here. Oops, that's kind of bad. You probably put like right here. And so this is just indicating this is the exact point at which the number of moles of like your base and your acid are equal. So if you go over that halfway point, it's right around 7. And so now that's the answer to your first question for like where their equivalence points are. And so this one is at, for graph 1, it's at 8, and for graph B, it's at 7. So the next question was, which one corresponds, or I guess first, before we go forward, does that make sense, or do you have any questions about like why the equivalence point is there, or like how I figured out halfway or anything like that?
No, that actually makes a lot of sense.
Okay, so then the next part of it is figuring out which of these is like corresponding to the strong acid titration, and which one is the weak acid titration. And so there's a few different clues here that we can look at. So one of the first clues is that the pH, the starting pH of this one, is a lot higher than the starting pH of this one. And if you remember, a stronger acid is going to result in a lower pH. So that's the first indication that this one is probably the strong acid. This one's probably the weak. But there's a few other like pieces that like can really like solidify that if you want to check yourself. So first, let's change all of this. So first, if you remember, like a weak acid cannot create a buffer. Like a weak acid, or sorry, that was wrong. A strong acid cannot create a buffer. A strong acid plus a strong base, they aren't going to do anything because they both just have spectators as like their conjugates, and so you can't have a buffer made out of them. And so like here on the strong one, you just kind of have like a curve that looks like this, like pH is like not really changing. Whereas on the other one, on the or it's like pH is changing a little bit, but it's not really like buffering. Like it's kind of like your curve is like, it's kind of like concave or convex. But over here on this side, your curve is like kind of like slowly increasing in pH because it's acting as a buffer here, because you have, every time you're adding in your strong base is reacting with your weak acid, it's creating some of your conjugate, and it's actually able to create a buffer in this section here. And so this section here is a buffer. And so that's why it increases a little bit. And so you see a difference in shape over here versus here, which is also indicative that this is weak and this is strong. The next thing is like the strong acid, because it hasn't been buffering, once you have the number of moles of acid equals the number of moles of base, which is your equivalence point, as you continue to add in acid, or as you continue to add in base here, the jump is going to be so huge because it went from not buffering at all to buffering like so much all of a sudden, where suddenly you no longer have any moles of H3O plus and you only have moles of OH minus because of really high pH. As opposed to here, you were able to buffer for a while. And so you were able to buffer, and then the jump isn't like that. It's still a big jump, but it's not like a huge jump. So that's another one. And then your last indicator that I think is helpful is if you remember like a strong acid plus a strong base, you do HCl plus NaOH, for example. Your Na plus is a spectator, your Cl minus is a spectator. They're going to dissociate all the way. You're going to end up creating H2O, and then you're just going to have your Cl minus and your Na plus being spectators in there. So the pH of the equivalence point when the moles of H plus and the moles of OH minus are the same is going to be, it's going to create only water. There's going to be 0 H plus, 0 OH minus, and there's going to be a ton of moles of H2O. And so the pH at your equivalence point is going to be the pH of pure water, which is 7, a pH of 7. But the pH of a weak acid at the equivalence point, you have all of your weak acid. So let's say HA is going to react with your strong base, which is, we'll put it as OH minus. And what happens here is that it ends up creating H2O to neutralize the weak base, or sorry, to neutralize the strong base, but then it also creates A minus. And so when you have so much of this OH minus at the equivalence point, when you have equal amounts of this and this, you're actually going to have a bunch of moles of A minus. And so what actually determines your pH is you using the KB of A minus. So when you have a weak acid concentration or a weak acid titration, the pH of the equivalence point is actually above 7 because the weak base is determining the concentration or the pH, and the weak base is going to be a little bit more basic than 7. And so that also indicates that it's going to be a weak acid for this one and a strong acid for this one. Does that help clear things up?
It does a little bit. I feel like I still just gotta like study this because I'm like still like a little confused.
Okay, and hopefully if we like go through a calculation, that might also help a little bit with some of the stuff. Do you guys, okay, so it's 3:47 and we went through the whole exam, so if you want to head out, you totally can, but if you have any other questions or you want to go through sorry, my brain thing. Or if you're gonna go through a titration problem, we can go through a full titration problem if that would be helpful too. Like the one that she gave you in class to do as a you do. Would you guys like
Yeah. Can we do that one?
Yeah, we can totally do that. Okay, so let me minimize this and let me pull up that. And I guess before we do that, are there any other questions about any of the stuff on the exam that you want to go over before we do the titration problem?
Yeah, I missed the first part. The second question on the stronger base, whatever. Could you explain that real quick?
Sure. So if you remember like your trends for acid.
Not that the second one.
Oh, this one? Or just this one?
Yeah, that one.
Oh, sorry. So if you have a stronger base, okay, so the stronger base is almost like the opposite of your conjugate acid. So if you remember, like how strong acids end up having really, really, really weak conjugate bases, like HCl. Cl minus is like so happy to be like hanging out with a negative charge on it that it doesn't need a proton. It's going to dissociate completely, so it's not going to like bond to H again here. So the stronger the acid, the weaker the conjugate base. And on the flip side of that, the weaker the acid, the stronger the conjugate base, because that conjugate base is really not stable, having that negative charge on it, and it really wants to have a proton again. So it's a bit of a stronger base because it's trying to grab a proton. And so in this case, it kind of goes back to our acid rules. So we have H2S versus H2SE. And so we look at these two, H2S versus H2SE. And so we can look at our periodic table here. And SE is larger in size than S. And so it's going to end up creating, it's going to be a larger atom than S will be, and since it's lower in the group, it'll have an extra electron shell. And so since Se is a larger than S, the bond will be weaker and the acid will be stronger because it's easier for that proton to leave. So H2Se is the stronger acid and H2S is the weaker acid. Remember, we just went over how the weaker the acid, the stronger the conjugate. And so because H2S is the weaker acid, it's actually the stronger conjugate. And so in this case, S2 minus is the stronger base. You can also just think of it in terms of like the S2 minus is less stable by itself, so it needs that proton to be stable. So it's trying hard to get a proton, so it's a stronger base.
All right, that makes sense.
Okay, cool. Okay, so let me go to the UDO problem. sorry. Okay. So, just trying to find it. Okay, here it is. So we can just check to make sure that we get the right answers here. But so the first thing to do is find the pH of the analyte. So the pH of the analyte. So okay, so do you guys remember what the constant or what analyte versus titrant means? Okay, in this solution or in this case, do you remember what an analyte is? Oops, sorry. Do you know what the analyte would be?
No.
Okay, that's okay. So in this case, the analyte is going to be, here, I'll just do it on Zoom. Okay, so in this case, the analyte is going to be the CH3, CH2, and H2. And the idea of the analyte, have you guys like seen pictures of what a titration looks like or anything? Ever?
No, I don't think.
So it's kind of, I feel like it's so, like I know that they can't have you guys doing labs right now, but even normally they don't have you guys do labs at the same time as chem, which I feel like is so, it makes it so much harder to understand because you have no idea what it looks like in a lab. So let me just Google like a picture of a titration so you can see what it looks like. And then hopefully you can like kind of understand. I spelled it wrong, okay. And so a titration, the idea of it is that here's what it looks like if you were to like do it in a lab. And so there you have like, okay, so you have like a beaker and then you have this easier picture. You have this beaker here. You have like a burette, which is looks like a tube. And then the burette is like able to like just release it like drop by drop by drop in. So you can make super specific measurements. And a lot of times you like measure pH throughout the entire time or throughout certain points. You can like create one of those pH like curves for a titration curve. And so the idea is that the analyte is the thing, like you know how much analyte you have the entire time. The analyte concentration is the same the entire time. So it's like usually you have usually the weak base or the weak acid goes here, and then the strong base of the strong acid goes here. And so the analyte is what's in a test tube that's like being, or it's in like the beaker, and then the like strong acid or strong base that you're dripping in goes into the analyte, or goes into the burette and is the titrant. This is the analyte. And so the idea of it is like you drop it like really, really slowly, and then because you know that you can like measure the pH if you were in a lab, you can determine what the concentration is of one of these, either the thing that's in the burette or the thing that's in the flask here. You can determine the concentrations. If you had like an unknown substance, you could determine what the concentration of it was, or what its identity was, depending on like where the equilibrium or the equivalence point was. And so the analyte is like what you have in your flask, and your titrant is like what you're adding into that flask. Does that make sense? Does that help at all, like having any context for what's happening? Or not really?
Yeah, I didn't actually know what the analyte and the titrant really was to begin with, so that.
So that's okay. So that's good at least a little bit to have like an idea of that. So the titrant here. So basically, like if we had if you were like doing a little lab experiment here, you'd have like a little beaker. I don't even know what happened there. You'd have like a little beaker, and it would be full of this CH3NH2, and you'd have 30 milliliters of it. So you'd fill up to 30. You'd have 30 milliliters of it, and it would be your CH3, CH2, NH2. And then you'd have a little burette above, and it would slowly drip a little bit of your acid in piece by piece. So this is where your HBr would go. So hopefully that like helps you like paint a little bit of a picture of like what's actually happening like in this experiment here. And then throughout the entire time, you're going to calculate the pH, but you could also be measuring the pH if you were actually in the lab. And so the idea here is that you would like solve for the pH at each point in this. And so the first point of it is the initial pH, which means you have not added any of your acid in. It's only the analyte. And so the analyte is like what's sitting in your beaker. So if you were to put a little like pH, they have like little like pH like measurers, which are basically just kind of just look like little like almost look like markers that you like put them in, and it tells you what the pH is. They're like called like pH wands. So you put the pH in, and it just tells you what the pH is. So if you hadn't added any acid in yet, you put it in the space, what would be the pH? And so the way that you would do it is, what is this substance? Is it a strong acid, a strong base, a weak acid, a weak base? What is CH3, CH2, NH2? You're given a Kb value, and it's going to react with HBr. Does that give you any hints on what CH3, CH2, NH2 is? If it's a weak or a strong acid or base?
Oh, weak base.
Exactly.
Yeah.
Okay. Yeah, exactly. So if it's a weak base, you're going to have CH2, or sorry, CH3, CH2, NH2. And you might be like, okay, what is it reacting with? But don't overthink it too much. It just goes back to like your like classic, if you remember like doing a lot more of these probably with acids, but just like your classic weak base solute like problem here. So you have a little bit of this like this substance in a solution, but mostly you have a bunch of water in the solution as well. So in order to get the pH, you're going to see how this substance reacts with water. And so it's only going to partially dissociate, and you're going to get a Ka value. So what happens here is that this is a weak base, and this nitrogen is able to take on another proton. So you end up actually creating CH3, CH2, NH3 plus, and OH minus. And so if you remember again, it's just like how we had done the weak acid things, your water is liquid, doesn't get included in your equilibrium expression. So you have your Kb equal to your concentration of OH minus this CH3, CH2, NH3 plus, over your weak base, your CH3, CH2, NH2. Okay, do we follow so far? Does that make sense? Do you have any questions about like how I got here, how I need to do that, anything like that?
No, that makes sense.
Okay. Kelly, are you good too?
Yes.
Okay, so now you have this in, you have your concentration of your weak base, right? You have it's 0.3 molar. And then you can just do small x approximation and do x and plug in x for this, because if you were to do an ice table, you have your initial, your minus, and whatever concentration of CH3, CH2, NH2 that you used, you would end up adding that and creating CH3, CH2, NH3 plus, and OH minus. And so we can simplify this to being x squared over our initial concentration, which is 0.3 molar. Sorry, 0.3 molar equals to our Kb value, which is 5.6 times 10 to the negative 4th. And so to solve for our x value, we would do the 0.3 molar times your Kb value, and then you would square root. So we would do 0.3 times 5.6 times 10 to the negative 4th, and you would get 1.68 times 10 to the negative 4th. You'd square root that, and your x value, x equals to 0.01, I'm just gonna say 0.013. Okay, so I'm gonna erase all of this. Is that okay if I erase this?
Yeah, it's fine.
If you erase it, for x, okay. So then to solve for POH, because remember this is our equation here. So we're producing OH. So x is equal to the concentration of OH. So we could do POH equals negative log of that value. And so POH is going to be negative log of that 0.013 and I got 1.88 for that. And then because we want to solve for pH for it, we just need to do 14 minus 1.88. And so 14 minus 1.88 is 12.11. So that's how you get the pH of the first part. Oh, also, if you were to do, if you do like 0.013 over the initial concentration over 0.3 and multiply by 100, you get 4.3%. So it's okay to use small x approximation for this one. Is there any questions first about how to get that first value, that 12.11? Does that make sense? Or do you have any questions?
Yeah, I have a question. Where did the 1.88 come from?
That was your negative log of your concentration of OH minus, which is your POH. And so when I did negative log of 0.01, I didn't put 0.13, I did like the actual value. And then I got I guess it was 1.89, but
Okay.
yeah, so I guess it's actually 1.89. Does that make sense? Is that good? That's where. Okay, is that good still, Kelly? Then if you use that?
Yeah, it makes a lot of sense. Thank
Okay.
you.
Okay, so now we have that. Okay, so we figured out the initial pH. So I'm going to erase all of this. And then obviously it's past 4, so if you want to go, feel totally free to go. And then the pH at the halfway equivalence point. Do you want to go? I think that she went over this. Do you guys want me to still go through it? Or not, I'm sorry, I think she went over the equivalence point, so I'll go over the halfway to equivalence point. Okay, so the halfway to equivalence point is going to be, so if you remember, the equivalence point is when the moles equal each other, when the moles of H3O plus or of your like acid that's added equal the moles of your weak base in this case. So the moles of HBr are going to equal the moles of your weak base, which is your CH3, CH2, and H2. And so let me add in. So just to before we proceed with this, whenever I'm writing about the HBr contribution, I'm just going to write it as H3O plus. And the reason for that is that HBr is going to dissociate completely. It's going to go HBr in water plus water, and it's going to end up just creating Br minus as a spectator, and it'll create H3O plus. So whenever I write about adding in the HBr, I'm going to write it as H3O plus, okay? So like here when I'm saying plus H3O plus, we're going to talk about it in terms of adding in HBr. Does that make sense and everything? Is that okay?
Yeah.
Okay. And so for this next step here, we're adding HBr, which I'm writing as H3O plus, to our weak base here. And so we're working in our halfway equivalence point. And so at our halfway equivalence point, we're going to have half of the moles of CH3, CH2, and H2, or like we're going to have them, the moles of this are going to be half of the moles of this. And so, or sorry, it's going to be 2 times the moles of H3O plus will be half of the moles of CH3 and H2 plus. And so that's just because at the equivalence point, they're equal. At the halfway point, half of the number of moles of acid have been added in to completely neutralize the base. And so at your halfway point here, you are going to create your CH3, CH2, and H2 is going to react with CH3O plus to create CH3, CH2, and H3 plus, and then it'll also create water. Okay, and so now I have to figure out how many moles are actually being added in, right? Because like we have we have our moles of our base, and we but like we don't know how much it's going to change by how much acid we're adding in, but we know it's supposed to be half of the equivalence point. And so in order to the first thing we have to do is figure out a number of moles of our base. And so we would do 0.030 liters, because that's just, that would be like it converted to liters. So 0.030 liters times our concentration, which is 0.3. And so that of the 3 molar, which gives us 0.03 times 0.3 gives us 0.009 moles of this base here. And so our starting point here is going to be our initial. So I'll do initial, change, and then EQ here. Okay, so draw a line. So our initial here is going to be 0.009. And then if you remember, it's the halfway point. It means half of the acid has been added in. And so it's going to be, the acid is going to be half of the value of this. So if you do 0.009 divided by 2 is 0.0045. And so you'll subtract out of the two of these, H3O plus is the limiting reactant, right? So you would subtract 0.0045 from both sides over here because it's going to react. And then you'd subtract it over here, 0.0045. And then the water doesn't really matter, but we're going to have, we initially have a concentration of 0, and we're going to be adding in 0.0045. So we end up actually creating 0.0045 moles of our weak acid. We have 0 H3O plus left, and we have 0.0045 moles of our weak base left. So now we have, so first, I guess, did this ice table make sense and everything? How I got these numbers, how all of that, does that make sense?
And you got the 0.0045 because it's half, right?
Exactly. So the halfway to equivalence point is just half of the concentration of your weak base. Or like half the amount. But does that make sense? Is it okay?
Yeah.
Okay, so now we have 0.0045 moles of our weak base, and we have 0.0045 moles of our weak acid or our conjugate acid. So what do we actually have here? If we have some moles of our weak base, we have some moles of our weak acid, or our conjugate acid, and they're pretty similar. In this case, they're the exact same amounts. What do we have here?
Is this when you use the Henderson equation or no?
Yep, exactly, because now it's a buffer, right? Does it make sense that it's a buffer right now?
Yeah.
Okay, so yes, now we have a buffer. We have 0.0045 moles of each of these substances. And so we can use our Henderson. I'm going to erase the ice table here, but I'll leave the equation because we're going to need it still. So now we have 0.0045 moles of each of these substances. So our Henderson-Hasselbalch, if you remember, is pH equals pKa plus log of our base, A minus, over the conjugate acid, HA. And so in this case, we're going to have, well, first, I guess, we're given a KB value. We need our pKa. So we have to go from KB to Ka. How do we solve for KB, or how do we solve for Ka from Kb? Do you guys remember?
A to the KW is equal to Ka times Kb.
Exactly. So we'll just do, if you remember, Kw is 1 times 10 to the negative 14th. We'll do 1 times 10 to the negative 14th divided by our Kb value, which is 5.6 times 10 to the negative 4th. And so 1 times 10 to the negative 14th divided by 5.6 times 10 to the negative 4th equals 1.8 times 10 to the negative 11th. I'm going to take the negative log of that in order to get our pKa value. And our pKa value is going to be 10.75. And then we could do negative log of our A minus, and that was 0.0045 moles. We don't need to find the constant, the volume of it, because it's going to cancel out in the Henderson-Hasselbalch equation anyway, because it's a ratio anyway. But if you have 0.00, so you can either write this out and you can actually put in your calculator. But if you remember, if you have the same amount on top of something, you're gonna cancel out. You're gonna create 1. We have 0.0045 over 0.0045. You're gonna cancel out, and you're actually gonna end up creating like log of 1, and log of 1 is going to end up being 0. So if you put this in your calculator and you do log of 0.0045 over 0.0045, this is going to go to 0. And so you'll find that in this case, your pH is going to equal your pKa. And so at the halfway equivalence point, you're going to have 10.75 as your pH. Do you guys have any questions about that?
No.
Okay. Bruce, does it sound good? Okay. Awesome. Okay, so before I go on to the to number 3, we're going to do number 4 because I can use the same equations that I have and stuff here. So if you had to, because you have 30 milliliters of 0.30 molar, and you're adding in 0.30 molar HBr. If you need the same number of or the amount of acid as you do base, how many milliliters of HBr are you going to need to create, or to get to the equivalence point with 30 milliliters of 0.30 molar CH3, CH2, and H2? How many moles of, or how many milliliters of this are you going to need to equal how much is here? They already have this in concentration.
Wait, can you say it one more time?
Yeah, so at the equivalence point, you have your the number of moles of your acid and number of moles of your base have to be the same. So you are going to have 30 milliliters of 0.30 molar of your base. You have that the entire time, but you're adding in progressively more of your HBr. So, and your HBr is a titrant. So it says titrant here, it's saying how much HBr is being added in. So I guess at what how many milliliters of HBr are you going to have to add to this in order to reach the equivalence point? And your equivalence point is when your number of moles are the same thing. How many milliliters? This is the same concentration, so you don't have to do any math for this. You need this value to equal this value. So you need they already have the same concentration. So how many milliliters do you have to put in of HBr to equal the number of moles you have from 30 milliliters of 0.30 molar?
Would it be 4 then?
It would be 30 because you would have to have the exact same concentration of HBr as CH3, CH2, NH2.
Wait, that wait, I'm confused.
Sorry, separately from, yes, Kelly, if you were saying you already added in 26 milliliters to get up to the equivalence point from here, you have to add 4 more in. Yeah, that's totally correct. You would need 30 milliliters of HBr total. Does that make sense? Is that what you were saying?
Yeah, that's what I was saying. Okay,
I'm so sorry. Yeah. Okay, yeah. So you would need 4 more to get to 30. Exactly. Okay, so so if you only have added 26 in yet, you're not at the equivalence point yet, right? So it's still going to be a buffer because at the equivalence point, you're going to have used up all of your weak base and converted it all into your conjugate acid. But at your like before that point, you're still going to have some of your weak acid and some of your conjugate base left, just like you did at the equivalence points. You can use Henderson-Hasselbalch and like the pKa and everything, and like the Henderson-Hasselbalch, so you would use just like this. Does that make sense what I'm saying?
Yeah.
Okay, so at this point, you'd have 26 milliliters of titration added in. Okay, so your titration is your HBr. You'd still have that 0.009 moles of your weak base would still be there, because each of these times, like, it's just kind of acting like you're, you know, they're not like compounding on each other. It's just like, okay, we have this much, we're adding 26 in. So you still have 20 or 0.009 moles of your CH3, CH2, NH2. We need to figure out how many moles of H3O plus you have though. So you're going to do 0.026, because that's when you do 26 divided by 1,000, you get 0.026. So 0.026 times 0.3 molar HBr, you should get 0.0078 moles of H3O plus. And you have 0 moles of your CH3 and H3 plus, and your water doesn't really matter. And so which one is the limiting reactant here? Is it the CH3, CH2, NH2, or the H3O plus?
Wait, I'm sorry. Under the H3O plus, is that 0.0078?
Why is it 0.0078?
Yeah.
I'm looking at number 4 right now. And that's because you would do 0.026, which is like the milliliters converted into liters, times the concentration of HBr, which is 0.3. So I did 0.026 times 0.3, and I got 0.0078.
Oh, okay. Thank you.
Yeah, okay. And then which one is gonna be your limiting reactant then if you have 0.009 moles of the base and 0.0078 moles of hydronium? Which one will be the limiting?
The hydronium.
Exactly, yeah. So you'll do minus 0.0078. And if you do that here, 0.0078. And then you'd add it to your conjugate acid. And so and so you'd end up having your final concentrations will be 0.009 minus that, so 0.9. And so you'll have 0.0012 of that CH3, CH2, NH2, and you're gonna have 0 of this, and you're gonna end up having 0.078 or 0.0078 of your conjugate acid. And so we go back to Henderson-Hasselbalch. We already have our pK is still written here at 10.75, and then we just change what's inside the actual log expression here. And so it's still our A minus over our HA. So our HA, if you remember, is the CH3, CH2, NH3. So we do log. And it'll be, so that's log of 0.0078. And again, we can just do moles because it's, even if you put the liters in, they'll end up canceling out. So you do need concentration for this, but because they're gonna cancel out anyway, we can just plug in moles. So you do 0.0078 over 0.0012. And so in that case, it would be the log value, the log of 0.778 divided by 0.0012, that's going to equal 0.813. And then you have to add that to your pKa, which is 10.75, like we saw for before. And so this should be an overall pH of 11.56 at 4 here, or for number 4. Let me just confirm that. Oops, sorry. Wait. Oh, I made a mistake. I wrote the wrong thing. So it wouldn't be In the expression here, instead of doing, I did my conjugate acid over my conjugate base, it's your conjugate base over your conjugate acid. Sorry. So it would be 0.0012 divided by 0.0078. Now let me try again to make sure I get the same thing. Okay, so you get negative 0.819 or 81 point, sorry, your log of 0.0012 over 0.0078 is negative 0.813. And then if you add that to your pK, which is 10.75, you get 9.94 for this. So 9.94, which is what we have here too. Okay. Any questions about that one? I know we're way over 4 o'clock, so if you have to go, you can totally go and also record going over the rest of it. Do you have any questions about how we got that? Does that make sense? Are you confused about anything?
I understand.
Yeah, that makes sense.
Okay. So let me erase. Okay. Okay, so the next one, the equivalence point is, I would say, the most annoying calculation out of all of these, which is kind of saying something because all of these are pretty lengthy calculations. But your equivalence point is kind of a weird one. So what happens at your equivalence point is that you have equal amounts of your enolate and your titrant. So in this case, you're gonna have equal amounts of CH3, CH2, NH2, and of HBr. And so if they're equal, what would happen is that you'd have your CH3, CH2, NH2 would react with your HBr. And what's going to happen is that these are going to be the exact same amount. So so in this case, it would be 0.009, because if you remember, we saw for the concentration of the CH3, CH2, NH2. And so they'd both be 0.009. And so you would subtract 0.009 from both of them. And the same thing over here. And you'd end up getting 0. So you end up getting 0 for both HBr and for CH3, CH2, NH2. And what you're going to create is that you're going to create your conjugate acid, CH3, CH2, NH3 plus. Now you're going to create 0.009 moles of your conjugate acid. So you have 0, you're going to add that 0.009, and you're going to create 0.009 moles of that conjugate acid. So do you follow so far?
Yeah.
Okay. And Kelly, are you all good too?
Yeah.
Okay, so yeah, so at this point, we're creating our conjugate acid. But the thing is, like, if not like you can do like pH equals like 0 for your H3O plus concentration, it's going to give you the answer or anything. It's like, how do I calculate this pH now? And the thing is that what's really contributing to the pH right now is your conjugate acid that you just created 0.009 moles of. So now you have the CH3, CH2, NH3 plus, and now you have like an abundance of this. You have 0.009 moles of this. And so now it turns into like a classic Ka expression using this as your acid. And so it's going to react with the water in the solution that was just produced by neutralizing so much of the HBr and everything. And so you're going to have a classic Ka expression with CH3, CH2, NH3 plus. So it's going to react with water, and it's going to produce H3O plus and your, oopsies, and it'll create your conjugate base again, this CH3, CH2, and H2. Okay, do you follow for why that's happening and everything? Does that make sense?
Mm,
Not really.
yeah, wait, it's taking me a second.
Yeah, okay, so with it for a second and then we'll,
No, that makes sense.
okay, yeah. Okay, and Kelly, how are you feeling? Does it make sense or is it still kind of confusing?
No, I understand.
Okay, so now what we're gonna do is just like our classic Ka expression. So the one that we have to calculate here is our total volume. So if you guys remember how you guys were talking about, we need 30 milliliters of this to reach our equivalence point, right? We have 30 milliliters of the CH3 the CH3 CH2 NH2. So we have to add that up, and we have total. We do 30 plus 30 would be 60 milliliters total, which will be 0.060 liters. So just keep that in mind for now. But actually, I'm just gonna do that calculation right now. So we'll do 0.009 divided by 0.060, so that we're working within concentration, because when we go to plug it into the Ka expression, it has to be in concentration. So I'm just gonna do it right now to just make it easier. So if I do 0.009 moles, which is our initial value for the weak acid, 0.009 divided by 0.060, we're gonna get a concentration of 0.15. Did you guys all get that and everything? All good so far?
Yeah.
Okay, so we have 0.15, 0.150, I guess, molar here. And then our water doesn't really matter for our Ka expression again, because it's like, remember liquid doesn't get put into our Ka expression. So we just need really our H3O plus concentration and our concentration of our conjugate base here. And so we're going to just assume small x approximation here. So we're going to say there's a 0 concentration of both of these right now, because we've neutralized all of this. Do you remember how, do you remember how we had done like the 0.009 minus both of these, and then it ended up both of them being 0? So currently we have 0 of each of these in the solution. Does that make sense and everything? So we do minus x and then plus x, just like a classic Ka calculation.
Yeah, that makes sense.
How did you get the 0.150 molar?
Yeah, so do you remember how at the equivalence point you need to have equal moles of both?
Yeah.
So I got that from like doing, I got 0.009 by doing the just finding out how many moles of CH3, CH2 and H2 I would need. So we would end up creating that much of the conjugate acid. So it's 0.009 moles. And then in order to find the concentration, we need the total volume. So at the equivalence point, the moles of HBr equal the moles of CH3, CH2, and H2. And so you need to get the total volume. So you have 30 milliliters of this and 30 milliliters of this to equal the equivalence point, which is a total of 60 milliliters. We convert that to liters, which is 0.060 liters, divide 0.009 moles by 0.060 liters, and you get 0.15 molar.
Okay, thank you.
Yeah. Okay, so then we would have just a classic Ka thing here, and we're going to assume small x approximation again. So I'm going to, I actually don't want to clear everything. Just going to clear this. And so for our Ka expression, we would do Ka equals, I'm just going to write x squared, but x squared is going to be the H3O plus times the concentration of our weak base, CH3, CH2, NH2, over the initial concentration of our weak acid, which was 0.15 molar. The last one that we have to do before we can solve for our concentration is we have to solve for Ka, because we're given Kb. So we had done this again earlier, but I just didn't save it. So it would be like Kelly had said earlier, you do the autoionization of water and divide by your KB to get your Ka. So you do 1 times 10 to the negative 4th divided by your KB to get your Ka. So 1.1 times 10 to the negative 4th divided by 5.6 times 10 to the negative 4th. And you get 1.78 or 1.79 times 10 to the negative 11th. That's a 7. 1.79 times 10 to the negative 11. And when you solve for x, so you do this. And so you should get 1.64 times 10 to the negative 6 for your x value. Did you guys get that as well?
Yeah.
Okay. And that is the concentration of your H3O plus. And it's also the concentration of your CH3, CH2, and H2. And so the real contributor to your pH is that H3O plus, right? So just like a normal Ka expression, we're just going to do negative log of that 1.64 times 10 to the negative 6. And we get the pH, which is 5.79. And I guess just if you wanted to check to make sure you could use Smoll's approximation, because we had used Smoll's approximation here. If you do that 1.64 times 10 to the negative 6 divided by 0.15 times 100, it's 0.001%. So we're okay to use small x. Do you guys have any questions about at the equivalence point, how you find pH?
No, I don't have any.
Kelly, are you feeling good?
Yeah, I don't know why, like, I'm not understanding these calculations. How did you get 1.79 times 10 to the negative 11?
I did 1.0 times 10 to the negative 14th divided by 5.6 times 10 to the negative 4th to get my Ka value. So that 1.79 is my Ka value.
Oh, okay, okay.
Is that good?
Yeah.
And then when I solve for x, I got 1.64 times 10 to the negative 6 smaller.
Okay, and then how did you get the 5.79?
Yes, so at this, so this x stands for the concentration of H3O plus, and then it also is the concentration of your weak or for your weak base. But the real determiner of your pH in like a weak acid problem is that H3O plus. And so you just do negative log of your H3O plus value. So negative log of 1.64 times 10 to the negative 6.
Got it. Thank you.
Of course. And then thankfully the last one I think is the easiest. You have to solve for, so you'd have your concentration as so actually, so let's go back to our like original expression here instead of going back, because if we had done this just for the special case of the equivalence point, we need to go back to our like our original reaction, which is the CH3 CH2 NH2, because we're still adding in our acid. So our base needs to react with our acid. So we have CH3 CH2 plus, or CH3 CH2 NH2 plus our H3O plus. And so then we'd have our, we'd end up creating our weak acid CH3 NH3 plus, and we'd also create water. Oh, sorry, it's CH3 CH2. Okay, so then what would happen here is that you have, okay, so you start off with your 0.009 moles again. So you have 0.009 moles of this CH3, CH2, NH2. Same deal again, it's just the thing that we originally calculated. That's always staying the same, it's 0.009 moles of this value. But now we have to find how much H3O plus is going to be added here. So if we do 40 milliliters, we would do 40 divided by 1,000 times the concentration of HBr in order to figure out our concentration of H3O plus. Okay, so I got 0.012. Did you guys get that as well? I don't know, I guess, are you guys doing the calculations at the same time right now?
Hold up, I gotta do it right now.
What'd you say?
I'll do it right now. Just to check.
Oh, okay, you don't have to, I just didn't know if you guys were doing it along with me or not.
I stopped this, so I'm not gonna lie.
Yeah. So I got 0.012 for the concentration of H3O plus. And so at this point, you have to stick, your limiting reactant is your weak base. So you do 0.009 to subtract that from both of these. But there's still a lot of H3O plus left. And so you would add on here to this too, 0.009. And so the concentration of the number of moles of H3O plus that are still remaining are 0.012 minus 0.009. You get 0.003. Oh my gosh, 0.003 moles of H3O plus. And so the last thing that you have to do, 0.003 moles of H3O plus. Because you need your concentration, you have to add 40 milliliters from the titrant with their 30 milliliters of your analyte. So you get 70 milliliters, divide that by 1,000 to get it in liters. And you have to divide 0.003 moles by 0.07 liters. And you get a concentration of 0.0429. And then because it's a concentration of H3O plus, to get pH, you do pH equals negative log of that value. So negative log of 0.429. And that is, or sorry, 0.0429, 1.37. Okay, so that's how you do all of them. Any questions, anything? Okay. If not, am I good to clear everything now?
Yeah, I'm good.
Yes.
All right, awesome. Okay, we've gone like way over, so I hope that that was helpful. Definitely feel free to email me if you have any questions that you come up with as you're studying. And yeah, if you have other questions about the exam or whatever, I'll post the answer key to the mock exam, and I'm working on creating like little reviews like how I posted for the last exam too. So I'll post those once I have them finished too. But
Thank you.
yeah, of course. I'm sorry it went so long, but thanks for staying with. I hope it was helpful.
Very helpful.